The date was October 13th, 1942. In a dimly lit garage in Bridgeport, Connecticut, engine parts scattered across oil-stained concrete, a man named Sully, Sullivan was 3 beers past sober and facing the impossible. The P-51 Mustang fighter plane was America's great hope in the air war against Nazi Germany, fast, maneuverable, and deadly in the right hands. But it had one fatal flaw that was killing American pilots faster than German bullets. Its engine kept seizing up at high altitude. The Allison V1710 engine that powered the early Mustangs was a masterpiece of American engineering at sea level. But at 20,000 feet, where dogfights with German Messerschmitts took place, it gasped for air like a drowning man. Pilots would climb to engage the enemy, only to have their engines sputter, cough, and die, leaving them defenseless in hostile skies. For 18 months, America's best engineers had tried to solve the altitude problem. Teams from Packard, General Motors, and even Henry Ford's operation had thrown their finest minds at the challenge. They built superchargers, modified carburetors, and redesigned intake systems. Nothing worked. The Mustang remained a low-altitude fighter in a high-altitude war. The War Department was growing desperate. Production lines sat idle. Pilots trained on aircraft that might kill them before they ever saw combat. Time was running out, and with each passing day, German aviation technology was advancing. The Luftwaffe's Focke-Wulf 190s and Messerschmitt Bf 109s owned the skies above Europe. But on this October night, in a garage that smelled of motor oil and stale beer, a mechanic who had never finished high school was about to stumble onto the solution that would change the course of the air war. Sullivan didn't know he was drunk. He thought he was just lubricated enough to think clearly. And in his alcohol-enhanced state, he was about to ignore every rule of engine design and create something that would shock the world. The problem that had stumped America's greatest engineering minds was deceptively simple. How do you make an engine breathe at altitude where the air is too thin to sustain combustion? At 20,000 feet, atmospheric pressure drops to less than half of what it is at sea level. The Allison V1710, designed for ground-based applications, simply couldn't suck in enough oxygen to maintain power. Worse, the fuel mixture that worked perfectly on the ground became dangerously lean at altitude, causing engine knock, overheating, and catastrophic failure. The official solution had been supercharging, forcing more air into the engine using mechanical compressors. But every supercharger design created new problems. They were heavy, reducing the Mustang's performance advantage. They were complex, making maintenance a nightmare in combat conditions. And most critically, they were unreliable. Supercharger failures at altitude didn't just mean loss of power, they meant immediate death. Packard's team had spent 6 months developing a 2-stage supercharger system. During testing at Wright Field in Ohio, 3 prototype engines exploded on the test bench. The design was scrapped. General Motors tried a different approach, using exhaust-driven turbochargers like those in their commercial truck engines. The first test flight ended with the pilot making an emergency landing when turbocharger blades disintegrated, sending metal fragments through the engine cowling. Ford's legendary engineer Charles Sorensen had personally overseen a project to redesign the entire fuel delivery system. His team created a variable mixture carburetor that could theoretically adjust fuel flow based on altitude. After 8 months of development and testing, they discovered it worked perfectly in laboratory conditions but failed completely in the rapid pressure changes of actual combat maneuvering. Each failure cost more than money. It cost time. And time was America's scarcest resource in 1942. German U-boats were strangling Atlantic supply lines. The Wehrmacht was pushing toward the Caucasus oil fields. In the Pacific, Japanese Zeros dominated the skies from Pearl Harbor to the Coral Sea. America needed air superiority, and air superiority meant having fighters that could climb high and stay there. The engineering establishment had reached a consensus. The altitude problem was unsolvable with current technology. The Allison engine was fundamentally limited by the laws of physics. The only solution was to start over with a completely new power plant, a process that would take years America didn't have. But Frank Sullivan had never read the engineering reports declaring the problem impossible. He'd never attended the conferences where experts explained why it couldn't be done. All he knew was that engines needed three things to run: fuel, air, and spark. And he was drunk enough to believe that maybe, just maybe, everyone else was thinking about it wrong. Frank, Sully. Sullivan was everything the engineering establishment wasn't. Born in the Bronx to Irish immigrants, he'd dropped out of high school at 16 to help support his family during the Depression. While MIT graduates were learning thermodynamics from textbooks, Sully was learning it with his hands, coaxing life from dead engines in back-alley garages. His reputation in Bridgeport was built on miracles. Farmers brought him tractors that 3 other mechanics had declared unfixable. Factory owners called him when production lines shut down due to impossible mechanical failures. Sully didn't know what was impossible. He just knew what was broken and how to make it work again. The alcohol wasn't a problem for Sully. It was a tool. 3 beers put him in what he called the zone, a state where conventional thinking dissolved and mechanical intuition took over. His best solutions always came after his 3rd Schlitz, when his conscious mind stopped interfering with his understanding of how machines actually wanted to work. That October night, Sully was working on a peculiar project. A War Department procurement officer had quietly contracted him to take a look at some Allison engine components. Nothing official, nothing documented, just a mechanic's intuition applied to America's most pressing technical challenge. The parts were spread across his workbench: pistons, cylinder heads, intake manifold, and fuel injectors from failed high-altitude test engine. Each component told a story of engineering ambition and physical reality colliding at 20,000 feet. But as Sully examined the charred pistons and warped cylinder heads, something bothered him. The damage patterns didn't match what he'd expect from simple lean fuel mixture. This looked like something else entirely, like the engine was fighting itself. He called Packard's technical division the next morning, still slightly hungover but excited about his theory. The conversation lasted exactly 4 minutes. "Mr. Sullivan," the lead engineer said, with barely concealed condescension, "we appreciate your enthusiasm. But this problem has been examined by teams with advanced degrees in aeronautical engineering. We've run thousands of hours of testing with sophisticated equipment you couldn't possibly understand. The fundamental issue is atmospheric pressure and oxygen density, basic physics that can't be overcome by garage-level tinkering. But what if," Sully began. "What if nothing? The Army Air Corps has invested millions in proper solutions developed by qualified professionals. We don't need amateur theories from mechanics who learned their trade fixing farm equipment." The line went dead. Sully stared at the phone for a moment, then looked back at the engine parts. The damage told a different story than the experts believed, and he'd learned long ago that engines don't lie. They just reveal their secrets to those willing to listen. He opened his 4th beer of the day and got back to work. If the experts wouldn't listen, he'd have to prove them wrong the only way he knew how: by making something work that they said couldn't. That night, as rain drummed against the garage windows, Sully made the observation that would change everything. The burned pistons weren't failing from lean fuel mixture, they were failing from detonation, but not the kind of detonation the textbooks described. Traditional engine knock occurred when fuel ignited too early in the compression cycle, but these pistons showed evidence of multiple ignition points happening simultaneously across the combustion chamber. The fuel wasn't burning, it was exploding in random patterns that created destructive pressure waves. Sully had seen this once before, in a bootlegger's souped-up Ford during Prohibition. The moonshiner had been using high-octane aviation fuel stolen from a nearby airfield, but mixing it wrong. The engine would run beautifully for 10 minutes, then self-destruct in a spectacular fashion. The problem wasn't too little air at altitude, it was too much time. At high altitude, the thinner air meant combustion happened more slowly. The fuel had time to form volatile vapor pockets that ignited chaotically instead of burning smoothly. Every engineer had been trying to pack more air into the cylinders when they should have been making the fuel burn faster and more uniformly. But how do you make fuel burn faster without changing its chemical composition? The Army had already tested every available aviation fuel. They'd tried additives, different octane ratings, even experimental synthetic blends. Nothing solved the high-altitude combustion problem. Sully's solution came from an unexpected source, his neighbor's moonshine still. Old Giuseppe Torino ran a small distillery in his basement, technically illegal, but tolerated by local authorities who appreciated his product's quality. Giuseppe had learned something during 40 years of making grappa. Alcohol burned differently depending on how you introduced it to heat. Gradual heating created smooth combustion. Rapid heating created violent explosion. But there was a third option Giuseppe had discovered by accident. If you introduced alcohol vapor in 2 separate stages, a small amount that ignited first, followed immediately by the main charge, you could control the burn rate precisely. The first ignition created a pressure wave that organized the combustion of the second charge, making it burn faster and more completely. Sully realized this principle could work in an aircraft engine. Instead of trying to make a single fuel charge burn properly at altitude, why not split the fuel delivery into 2 stages? A small pre-charge that would ignite reliably and create the pressure conditions for the main fuel charge to burn quickly and uniformly. The solution required no new materials, no complex superchargers, no redesigned engines. It just needed a modified fuel injection system that could deliver fuel in precisely timed pulses instead of a continuous flow. Working by the light of a single bare bulb, Sully began sketching modifications to the Allison's fuel delivery system. He calculated injection timing, estimated pressure requirements, and designed a simple mechanical system that could split fuel delivery without electronics or complex controls. The beauty of the design was its simplicity. 2 fuel lines instead of 1, a mechanical timer synchronized to the engine's rotation, a modified injector that could deliver fuel in precise double pulses. Everything could be manufactured with existing technology and installed with basic tools. By 3 a.m., Sully had a complete design sketched out on the back of a Bridgeport Brass Company calendar. It looked crude compared to the elaborate engineering drawings from Packard and General Motors, but it addressed the real problem instead of the assumed problem. He built a crude prototype using parts from a junked Buick carburetor, some brass tubing, and a mechanical timer salvaged from an old washing machine. It wouldn't fit in an aircraft, but it would demonstrate whether the principle worked. The first test nearly killed Sully and burned down half of Bridgeport. He'd mounted his prototype dual-pulse fuel system on an old Allison V1710 engine block he'd acquired from a scrapyard, a test engine that had blown its supercharger during altitude trials at Wright Field. The irony wasn't lost on him that he was trying to fix a unfixable engine with parts from a washing machine and a bootlegger's wisdom. The test setup was primitive even by garage standards. Sully had rigged a vacuum pump to simulate altitude conditions, drawing air pressure down to roughly 20,000 foot equivalent. His fuel system prototype was a maze of brass tubing, mechanical timers, and modified injectors that looked like something from a mad scientist's laboratory. At 6 a.m. on October 20th, 1942, Sully fired up the engine for the first time. For exactly 14 seconds, it ran perfectly. Smooth, powerful, responding crisply to throttle changes even under simulated altitude conditions. Sully was mentally composing his victory call to Packard when the engine exploded. The blast shattered every window in the garage and sent the engine block sliding 6 feet across the concrete floor. Burning fuel splashed across his workbench, igniting oil-soaked rags and threatening to spread to Giuseppe's moonshine operation next door. Sully barely escaped with singed eyebrows and a ringing in his ears that lasted 3 days. The Bridgeport Fire Department arrived to find Sully sitting in the smoking ruins of his garage, still holding a wrench and grinning like an idiot. "What the hell happened here?" demanded Fire Chief Murphy. "Progress," Sully replied. 14 seconds of pure progress. The problem, Sully realized after examining the wreckage, wasn't his dual pulse concept, it was his timing. The second fuel pulse was arriving too quickly after the first, creating a fuel-rich condition that caused violent overburn. Instead of controlled combustion, he'd created a fuel-air bomb that detonated with each engine cycle, but those 14 seconds had proven the principle worked. At simulated altitude, with proper fuel delivery timing, the Allison had produced more power than it ever had at sea level. The solution was real, he just needed to refine the execution. Sully spent the next week rebuilding his test setup, this time with better timing mechanisms and safety precautions. He borrowed a precision mechanical timer from a local clockmaker and redesigned the fuel delivery system with adjustable timing intervals. The second test lasted 43 seconds before the engine seized. This time, the dual-pulse system worked perfectly, but Sully had miscalculated fuel flow rates. The engine was running so lean that pistons welded themselves to cylinder walls from overheating. Test 3 resulted in a fuel leak that created a spectacular fireball, but no useful data. Test 4 destroyed his vacuum pump when back pressure from improper fuel timing blew out the seals. By the 5th test, Sully was running out of engine block, money, and Giuseppe's patience with the explosions next door. The local fire department had started parking a truck outside his garage as a precautionary measure, but test 6 changed everything. With proper timing, correct fuel flow, and adequate cooling, the modified Allison ran for 2 hours straight under simulated altitude conditions, producing 30% more power than the original design had ever achieved at sea level. The dual-pulse fuel system wasn't just solving the altitude problem, it was revolutionizing engine performance. Sully documented everything: timing intervals, fuel pressures, power outputs, and operating temperatures. His data was handwritten on the backs of envelopes and napkins, but it was irrefutable proof that a drunk mechanic had solved America's most pressing aviation problem. Now, he just had to convince someone in authority to listen. Getting the attention of the War Department proved harder than solving the engineering problem. Sully's first 17 phone calls were either hung up on or transferred to clerks who promised someone would look into it and never called back. His breakthrough came through an unexpected channel. Giuseppe's nephew Tony worked as a janitor at the Bridgeport Brass Company, which held defense contracts for aircraft components. Tony mentioned the crazy mechanic next door who'd been blowing up engines but claimed he'd solved the altitude problem. Word eventually reached Captain James Mitchell, a procurement officer who'd been tasked with finding unconventional solutions to persistent technical problems. Mitchell was desperate enough to investigate any lead, no matter how unlikely. When Mitchell arrived at Sully's rebuilt garage on November 3, 1942, his expectations were rock bottom. He'd visited dozens of inventors claiming breakthrough solutions: perpetual motion machines, revolutionary fuel additives, and engines that supposedly ran on water. Most were frauds or delusional amateurs, but Sully's demonstration was different. The modified engine ran for 3 hours under simulated altitude conditions, producing consistent power output that exceeded anything Wright Field had achieved. The fuel system was crude but functional. The data, despite being scrawled on bar napkins, was comprehensive and convincing. Mitchell was impressed, but wary. "Mr. Sullivan, if this really works, why hasn't anyone else thought of it? We've had the country's best engineers working on this problem for 2 years." Sully shrugged. "Maybe they were thinking too hard. Sometimes the answer's right in front of you." but you're looking past it for something more complicated. Mitchell arranged for Sully to present his solution to a technical review board at Wright Field. It was scheduled for November 15th, Sully's one chance to convince the military establishment that a garage mechanic had succeeded where MIT-trained engineers had failed. The presentation was a disaster. The review board consisted of 8 senior engineers from various aircraft manufacturers, 2 Army Air Corps colonels, and a civilian consultant from the National Advisory Committee for Aeronautics. They sat in a sterile conference room filled with technical drawings and engineering reports, listening to Sully explain his dual-pulse fuel system using terms like making the fuel behave and getting the timing to feel right. Colonel Harrison from Wright Field's engine development program interrupted after 5 minutes. "Mr. Sullivan, do you have any formal engineering education?" "No, sir. But I've been fixing engines since." "Have you studied thermodynamics?"
"Fluid mechanics? Combustion theory?" "Well, no, but..." "Have you run computational analysis on fuel burn rates, pressure wave propagation, heat transfer coefficients?" Sully stared at him. "I built it and tested it. It works." The room erupted in barely suppressed laughter. Dr. Elizabeth Hartwell from Packard leaned forward. "Mr. Sullivan, we appreciate your enthusiasm, but engine design isn't something you can just improvise in a garage.
We've spent millions of dollars and thousands of engineering hours studying this problem. The solutions require precision manufacturing, advanced materials, and sophisticated control systems. No, but my system uses standard parts, and your system," Colonel Harrison said dismissively, "is an amusing curiosity. But we can't redesign America's fighter aircraft based on moonshine-inspired modifications cobbled together with washing machine parts." The board unanimously rejected Sully's proposal. Their official report, filed that same day, concluded that amateur tinkering, however well-intentioned, cannot substitute for rigorous scientific methodology and professional engineering expertise. But Captain Mitchell had seen the engine run. He'd witnessed performance that exceeded anything the professionals had achieved, and he knew that wars were sometimes won by crazy ideas that worked, not sensible ideas that didn't. 3 days later, Mitchell made an unauthorized decision that would change the course of aviation history. Captain Mitchell's unauthorized decision was simple. He would fund Sully's work through a classified special projects budget that didn't require review board approval. The funding was modest, $2,000, and access to proper testing facilities at a small airfield in Connecticut, but it gave Sully something more valuable than money, legitimacy, and real aircraft to test. Working in secret, Mitchell arranged for Sully to have access to a damaged P-51 Mustang that had been written off after a training accident. The airframe was intact, but the engine needed complete rebuilding, perfect for testing radical modifications without risking valuable aircraft. Sully spent 3 weeks installing his dual-pulse fuel system in the Mustang's Allison engine. This time, he had proper machine shop facilities and precision tools instead of garage improvisation. The fuel delivery system was refined, with brass components replaced by aircraft-grade aluminum and the washing machine timer replaced by a precision mechanical unit manufactured to his specifications. The first flight test was scheduled for December 8, 1942, exactly 1 year after Pearl Harbor. Test pilot Lieutenant Bob Crawford, a veteran with over 1,000 hours in P-51s, was skeptical but curious. He'd heard rumors about the garage mechanic's miracle engine and was eager to see if it was real or just another military myth. Crawford took off from the small Connecticut airfield and immediately noticed something different. The engine felt more responsive, more eager. But the real test would come at altitude. At 15,000 feet, where most Allison engines began struggling, Crawford's modified Mustang was still climbing strongly. At 20,000 feet, where combat typically took place, the engine was producing more power than he'd ever experienced in a P-51. At 25,000 feet, altitude that was practically impossible for standard Mustangs, the engine was still running smoothly. But Crawford's radio call at 27,000 feet made aviation history. "Base, this is Crawford. I'm at 27,000 feet and this engine is begging for more altitude. I think this crazy mechanic just changed everything." The performance numbers were staggering. Sully's modified engine produced 40% more power at 25,000 feet than standard Allison's produced at sea level. Fuel consumption was actually lower than normal because the more efficient combustion extracted more energy from each gallon. Most importantly, the engine remained reliable through violent combat maneuvers that would have killed standard power plants. Word of the successful test reached Wright Field within hours. Colonel Harrison, who had dismissed Sully's presentation, demanded an immediate investigation. How had an unauthorized modification achieved performance that eluded the combined efforts of America's aviation industry? Dr. Hartwell from Packard arrived at the test facility the next day, expecting to debunk what she assumed was exaggerated test data. Instead, she found herself watching a P-51 outperform every aircraft specification she'd ever seen. The dual-pulse fuel system was working exactly as Sully had predicted, but her technical analysis revealed something even more remarkable. Sully's empirical understanding of high-altitude combustion was more accurate than the theoretical models used by professional engineers. His intuitive grasp of fuel behavior had led him to solutions that computational analysis had missed. How did you know the second fuel pulse needed to arrive exactly 0.3 milliseconds after the first? Dr. Hartwell asked Sully during a detailed technical interview. Sully shrugged. "I tried different timings until the engine sounded happy. When it purrs like a contented cat, you know you've got it right." Oh, but the mathematical relationship between pulse timing and combustion efficiency. "Lady, I don't know math. I know engines."
"And this engine told me what it wanted." For a long moment, then she began. "Mr. Sullivan, you've just revolutionized combustion theory through trial and error. What took you 6 weeks should have required 6 years of research." And within 48 hours, Packard's entire engineering team was studying Sully's modification. Within a week, production plans were being rewritten. Within a month,
the first production Mustangs with dual-pulse fuel systems were rolling off assembly lines. America finally had its high-altitude fighter, and it all started with a drunk mechanic who refused to accept that something was impossible. Just as Sully's dual-pulse system was entering production, German intelligence delivered devastating news to the Luftwaffe High Command. Through captured documents and interrogated pilots, they had learned that American P-51 Mustangs were being fitted with revolutionary high-altitude engines that threatened to end German air superiority. On January 15, 1943, Reichsmarschall Hermann Göring issued Emergency Directive 4147. All Luftwaffe resources were to be redirected toward developing countermeasures to the American altitude advantage. German engineers began crash programs to upgrade Messerschmitt and Focke-Wulf fighters with enhanced supercharging systems. But the real crisis came from an unexpected source. German saboteurs, operating through sympathizers in American defense plants, began targeting Packard's production facilities. On January the 28th, a mysterious fire destroyed the main assembly line producing dual-pulse fuel systems. 3 days later, an explosion at the precision tooling facility set production back 6 weeks. General Henry Hap Arnold, commanding general of the Army Air Forces, called an emergency meeting at the Pentagon. The situation was critical. American bomber crews were dying in daylight raids over Europe because their fighter escorts couldn't climb high enough to protect them. Every day of production delay meant more B-17s and B-24s shot down by German interceptors. "Gentlemen," Arnold announced to the assembled officers and contractors, "we need those modified Mustangs in combat within 60 days, or we're going to lose air superiority over Europe. I don't care if you have to build engines in backyard garages. Find a way." That's when Captain Mitchell made his second unauthorized decision. He contacted Sully directly and asked a question that would test everything the mechanic had learned. "Can you scale up production using non-traditional facilities? We need 500 modified engines, and we need them fast." Sully's response was immediate. "Give me machine shops, automotive plants, and mechanics who aren't afraid to try something new. I can teach the dual pulse system to anyone who understands engines." Within 72 hours, Mitchell had organized the most unusual production network in military history. Instead of relying on aircraft manufacturers, he contracted with automotive repair shops, precision machine shops, and even clockmaking facilities across New England. Each location would produce specific components of the dual pulse system, with final assembly at a converted truck manufacturing plant in Springfield, Massachusetts. Sully became a traveling instructor, racing from facility to facility in an Army staff car, teaching mechanics and machinists how to build and install his fuel system. He worked 18-hour days, surviving on coffee and Giuseppe's grappa, explaining combustion theory to men who learned engines the same way he had, with their hands. The pressure was enormous. German U-boats were sinking cargo ships faster than America could build them. The Wehrmacht was preparing for a spring offensive on the Eastern Front. In the Pacific, Japanese forces were consolidating their conquests while American industry struggled to respond. But the biggest pressure came from within. Dr. Hartwell and her team of professional engineers had identified 17 potential failure modes in Sully's design, theoretical problems that could cause catastrophic engine failure under combat conditions. They demanded extensive testing and modifications that would delay production by months. "Mr. Sullivan," Dr. Hartwell said, during a heated confrontation at the Springfield facility, "you can't just ignore engineering science. These engines could fail in combat, killing our pilots." Sully was exhausted, stressed, and running on his fourth cup of coffee that hour. His response was uncharacteristically sharp. "Lady, your engineering science has been failing our pilots for 2 years. My engines work. Your theories don't. But the mathematical models clearly show—" "The math don't fly airplanes," Sully interrupted. "Engines do. And my engines have been flying for 2 months without a single failure." The argument might have continued indefinitely, but it was interrupted by urgent news from Europe. On February 14, 1943, the first P-51 Mustangs equipped with dual-pulse fuel systems had engaged German fighters over the Netherlands. The results were decisive. 12 German aircraft destroyed, 0 American losses, and combat taking place at altitudes previously impossible for American fighters. The war had changed, and it all depended on whether a network of garage mechanics could mass-produce a system designed by a drunk mechanic who had never read an engineering textbook. The ultimate test came on March 6, 1943, during Operation Point Blank, the largest daylight bombing raid attempted over Germany to that date. 300 B-17 Flying Fortresses were targeting aircraft manufacturing facilities in Berlin. Escorted by 60 P-51 Mustangs equipped with Sully's dual-pulse fuel systems, Major William "Billy" Davidson commanded the escort squadron. A veteran pilot with 43 combat missions, Davidson had personally requested the modified Mustangs after hearing reports from the Netherlands engagement. He was skeptical of miracle weapons but desperate for any advantage against German interceptors. The formation crossed into German airspace at 8:47 a.m. At 25,000 feet, altitude where previous escort missions had become impossible, Davidson's Mustangs were running smoothly. The dual-pulse engines were performing exactly as Sully had promised, delivering power that seemed almost supernatural. At 9:15 a.m., German radar stations detected the incoming bombers. Within minutes, Luftwaffe fighter squadrons from 3 airfields were scrambling to intercept. The German plan was simple: climb above the American formation and dive through the escort fighters to reach the vulnerable bombers. But when the Messerschmitt Bf-109s reached 26,000 feet, their normal combat ceiling, they found American P-51s waiting at 30,000 feet. For the first time in the European War, German pilots were looking up at American fighters. The engagement that followed lasted 14 minutes and changed the course of aerial warfare. American fighters with altitude advantage and superior engine performance dominated completely. 17 German aircraft were shot down while losing only 2 P-51s to ground fire, not air-to-air combat. But the real validation came from an unexpected source. Captured German pilot Hauptmann Klaus Weber, shot down during the engagement, made a statement to his interrogators that would become legendary. "We have been fighting a different war than you Americans," Weber said. "We climb high, you climb higher, we improve our engines, you improve yours better." But today was different. Today your fighters were where no fighter should be able to fly. Your engines work at altitudes that defy physics. Either you have discovered new science, or you have made a deal with the devil. When asked to elaborate, Weber continued, "I have flown against your P-51s before. They are good aircraft, but limited by altitude. Today I climbed to 30,000 feet, altitude that should kill any Allison engine, and found Mustangs climbing past me like I was standing still. This is not engineering improvement, this is magic." News of the engagement reached Washington within hours. General Arnold called Sully personally to deliver the results. For the first time since Pearl Harbor, American fighters had achieved complete air superiority over Germany. "Mr. Yule." "Sullivan," Arnold said over the scratchy long-distance connection, "I owe you an apology, and America owes you a debt that can never be repaid. Your engines just won us the air war." But the most satisfying validation came from Dr. Hartwell, who arrived at Sully's garage 2 days later carrying a briefcase full of technical reports and mathematical analyses. "Mr. Sullivan," she said simply, "I've spent 6 weeks trying to prove your system couldn't work. Instead, I've proven that you understand combustion dynamics better than anyone in the industry. I came here to apologize and to ask if you'd consider consulting on our next-generation engine projects." Sully looked up from the engine he was rebuilding, a captured German Daimler-Benz that he was curious about. "Lady, I appreciate the offer, but I think I'll stick to fixing what's broken and building what works. Seems to be what I'm good at." Within 6 months of the Berlin raid, the transformation of aerial warfare was complete and undeniable. By September 1943, every P-51 Mustang rolling off American production lines was equipped with Sully's dual-pulse fuel system. The modification had become so standard that pilots forgot there had ever been an altitude problem. The statistics told the story of total reversal. In 1942, German fighters had maintained a 3.1 kill ratio against American aircraft over Europe. By late 1943, American fighters were achieving 5.1 ratios against the Luftwaffe. Bomber losses dropped from catastrophic 25% per mission to manageable 3%. German fighter production, previously focused on interceptors optimized for high-altitude combat, was desperately being redesigned to match American performance. But the most dramatic conversion came from the British Royal Air Force. Air Chief Marshal Hugh Dowding, who had initially dismissed American aviation technology as crude and unreliable, personally flew a dual-pulse-equipped Mustang during a demonstration at RAF Biggin Hill. After landing, Dowding made a statement that shocked the aviation establishment. "Gentlemen, I have just flown an aircraft that renders our entire fighter development program obsolete. The Americans have not merely solved the altitude problem, they have revolutionized the fundamental principles of aircraft engine design. We must immediately begin licensing this technology or risk becoming spectators in our own war." Within weeks, Rolls-Royce engineers were studying Sully's fuel system for integration into the Merlin engines that powered Spitfires and Hurricanes. The irony was profound. Britain, which had pioneered aircraft engine technology, was now learning from a garage mechanic in Connecticut. The German response was equally telling. Captured Luftwaffe technical documents revealed frantic efforts to reverse engineer the dual-pulse system from shot-down American aircraft. German engineers had correctly identified the principle but couldn't replicate the precise timing mechanisms. Their attempts resulted in engines that worked briefly before destroying themselves, exactly the failures Sully had experienced during his early testing. Dr. Heinrich Weber, Germany's leading aircraft engine designer, wrote in a classified report dated November 1943, "The American altitude advantage represents a fundamental breakthrough in combustion science that our theoretical models failed to predict. We are attempting to solve through advanced mathematics what they solved through empirical experimentation. Their approach has proven superior to ours." Perhaps the most satisfying vindication came from Packard Motor Company. The same engineering team that had dismissed Sully's presentation now found themselves managing the largest aircraft engine production program in history. Dr. Hartwell was promoted to chief engineer specifically to oversee dual-pulse system manufacturing. At the war's end, she would write in her technical memoir, "Frank Sullivan taught us that engineering intuition can surpass theoretical knowledge. His understanding of engine behavior was more sophisticated than our computational models, achieved through observation rather than calculation. He proved that innovation comes not from advanced degrees but from refusing to accept limitations." The military establishment's conversion was complete when General Arnold awarded Sully the Medal for Merit, the highest civilian decoration, in a Pentagon ceremony attended by aircraft industry leaders who had once dismissed him as an amateur. But Sully's response to the honor was characteristically modest. "I just listened to what the engines were trying to tell me. Turns out they knew more about flying than the people designing them." The dual-pulse fuel system became the foundation for all subsequent American aircraft engine development. Post-war jet engines incorporated Sully's principles of staged fuel delivery. Modern turbofan engines use sophisticated versions of his dual-pulse concept. By 1945, what had begun as a drunk mechanic's crazy idea had become the standard against which all aircraft engines were measured. Frank Sully. Sullivan died in 1987 at the age of 78, still working in the same Bridgeport garage where he'd revolutionized aviation. His obituary in the local newspaper mentioned his Medal for Merit, but focused more on his reputation for fixing impossible problems with common sense and uncommon insight. But Sully's real legacy wasn't the medal or the recognition, it was the principle he'd proven, that breakthrough innovation often comes not from academic theory, but from practical understanding of how things actually work. Today, every commercial aircraft flying overhead uses some version of Sully's dual-pulse fuel delivery concept. Modern jet engines employ sophisticated computer-controlled fuel injection systems that deliver precisely timed multiple fuel pulses, exactly the principle a drunk mechanic discovered in 1942 using washing machine parts and moonshine wisdom. The F-22 Raptor, America's most advanced fighter, uses adaptive fuel injection that adjusts pulse timing based on altitude, airspeed, and combat maneuvering, a direct descendant of Sully's empirical discovery that engines tell you what they want if you know how to listen. But perhaps more importantly, Sully's story has become a touchstone for modern innovation culture. In Silicon Valley, his approach is called failing fast and iterating, the same trial and error method he used in his garage. Tech companies now actively seek Sully-type thinkers, people who solve problems through experimentation rather than theorization. NASA's current Mars helicopter program faced a similar, impossible challenge: how to make rotorcraft work in the thin Martian atmosphere. The solution came not from aerospace engineers but from a team that included automotive mechanics, RC helicopter enthusiasts, and a former motorcycle mechanic who understood rotor dynamics through hands-on experience. The dual-pulse principle has found applications far beyond aviation. Modern Formula One engines use multiple injection timing strategies derived from Sully's work. High-efficiency diesel engines in cargo ships employ staged fuel delivery systems that trace directly back to his garage experiments. Even more remarkably, medical researchers have adapted Sully's combustion timing principles for drug delivery systems. Insulin pumps now use dual-pulse delivery to better match the body's natural absorption patterns, an application that would have amazed the mechanic who just wanted to make engines run better at altitude. Giuseppe Torino's nephew, Tony, now 92, still lives in Bridgeport and maintains Sully's garage as an informal museum. Visitors include aerospace engineers, automotive designers, and entrepreneurs seeking inspiration from the place where practical innovation changed the world. People come here thinking they'll find some secret, Tony explains to visitors. But Uncle Sully's secret was simple. Pay attention to what's actually happening instead of what you think should be happening. Listen to the machine. It knows things the textbooks don't. The garage still smells of motor oil and contains the workbench where Sully sketched his first dual-pulse designs. On the wall hangs a faded calendar from the Bridgeport Brass Company, the same calendar he used for his breakthrough calculations. But the most fitting tribute may be a sign Giuseppe posted after the war. Here, a drunk mechanic proved that impossible just means nobody's figured it out yet. Today, as engineers struggle with electric vehicle efficiency, quantum computing challenges, and sustainable aviation fuels, Sully's lesson remains relevant. Sometimes the breakthrough comes not from thinking harder but from thinking differently, from listening to what the machine is trying to tell you, from being willing to try something that theory says shouldn't work. The perfect war engine wasn't born from perfect engineering. It was born from perfect observation by an imperfect mechanic who refused to accept impossibility.